So now we can proceed with the acceleration. Okay. So now you construct three pictures like this. General rigid body motion equals pure translation plus pure rotation. Okay. So for the rigid body motion, okay, for this link BD, just draw the accelerations at both ends. So AB goes straight to the left, as we found earlier. And then AD, acceleration at point D, you know that acceleration at point D is in the horizontal direction, okay, because the motion at point D goes this direction. But whether it is pointing to the left or right, we don't know. Okay? Although we do know from before that velocity of D goes to the right. Okay? But whether it is accelerating or slowing down as it is going to the right, we don't know. So just assume something. Okay? Once again, if we don't know something, assume a direction. Okay? So I'm going to assume that it is slowing down. Okay? As point D is going to the right. Right? It's slowing down, it's decelerating. So the acceleration vector is actually going to the left. That's my assumption. Okay. Pure translation, they use whatever that I know, which is AB that I found earlier. So as if this whole thing is translating, or it's slowing down at the same acceleration. Okay? So AB here and AB there. Pure rotation, since I picked point B as the known quantity as the reference for translation, so point B here will be fixed. So this picture is as if this link AB is rotating about point B, okay, or is accelerating about point B. So here you draw all the accelerations, okay? Or make the alpha, okay, angular acceleration, okay, for BD. Now, since I assume that this is going this way, okay, the acceleration of D is going to the left. So for this fixed, okay, point B, right, my angular acceleration, okay, is going to point in the counterclockwise direction. Okay. And I can also draw the angular velocity, omega BD, which is really what I'm looking for, is the unknown here. Okay. And the omega BD, the omega BD, okay, will be used for the acceleration up here, okay, for the normal component, which points toward the center, okay, point D, and then the tangent component of acceleration, okay, is perpendicular to the normal component, okay, going up this direction. So tangent component is R alpha, okay, alpha BD, and then R is this length right here, okay. And then for normal components, R omega square, and again R is 0.3, the length of BD, 0.3 meters times omega squared. Okay. So you write down the equation for point D. Alright, acceleration of point D equals pure translation, which is point B, alright, AB, plus these two guys right there. Okay? So this equation can be constructed by looking at this point D, right, in these three pictures. Right? AD equals AB plus these two. Right? And keep in mind, these should be vectors. Okay? The vector, tangent, and vector normal component. And then you just proceed to expand it. Keep in mind they're all vector, which means that there should be I and J components in there. Okay, so I can just build in I and J right away in the next step. So for AD, since I assume they're going to the left, so this will be the magnitude of AD and then direction, which is negative I. That's it, there's no J component. AB, I found it from earlier, which is 59.2176 radian per second, meter per second square, and it's going to the left, so it's negative I, plus this guy right there, the tangent component, which is pointing in this direction, okay, and the magnitude is 0.3 alpha BD, which is the unknown, okay, the unknown, and that's magnitude. What about the direction of this tangent vector? It's pointing this way, so you need to resolve it into I and j, and this is 36.86 degrees, which means that this is 36.86 degrees. So the direction would be I component is negative, sine 36.86 degrees. The y component is plus. I component plus cosine 36.86 degrees j. Okay, so this is my tangent component plus the last term. Normal component points down this way. Since this is 36, so this is also 36.86 degrees. And this is 0.3 omega squared, and omega BD has been found way earlier also from the instantaneous center method to be 7.854 radian per second. Now square of that. Okay, so that's my magnitude. So I need to add the direction of this vector, which is the I component is negative direction. So negative of cosine 36.86 degrees I, and then the y component goes straight down, so it's negative sine degree j. Okay, so I get I and j component all built in here. So here, the unknown, the only unknown, actually no, there are two unknowns here, right? So the AD, and we've got right here. But to solve for omega BD, since this other unknown is only in the I direction, I can just take the j component only. Okay? Just solving for j component, so I have 0, the left hand side, equals, this first term is 0, plus, okay, just look at the j component only, so 0.3 alpha BD cosine 36.86, and then plus 0.3 7.854 squared, and then minus sine 36.86 degrees. So, and then solve for alpha BD. So it turns out to be 46.266 radian per second squared. Alright. So I solve for alpha. Okay. So I solved for the first of the two unknowns that I need for the kinetics equation. Okay, you refer back to the last video. And for the forces, okay, the sum of moment equation, okay, I need alpha BD as well as acceleration of the center of gravity. Okay. Now here in this equation, it's AD, so it's of no use anymore. Okay, to us. Okay, so I don't need to find this. But instead, I want acceleration at center of gravity. Okay, so what do? Well, I need to then construct this whole picture and then this procedure again between B and G point. Okay, so basically just repeat the whole procedure. Okay, except you apply that for B and G.